But we're basically the product of the merger of two, what was Technicons back in 2005, and the satellite program that I'm involved with was established in 2009. Over the years, we've managed to also do workshops. And so we've managed to organize a few workshops. Then we're lucky enough to have quite nice facilities. We're housed in one of the two new electrical engineering buildings on campus. And then we're lucky enough to have our own clean room that we can do integration with. And we also use our clean room for the integration of ZQube2. And then we have a ground station that operates on amateur frequencies that we built in, I think, 2013 for the launch of ZQube1. So that's been running for a couple of years and desperately needs a bit of maintenance. And then I'll also show you a bit later the ground station that we constructed for ZQube2. So we do a few different things, one of which is we design, manufacture and sell subsystems for CubeSats. The first sort of, I guess, product that we started with was a UHF VHF transceiver that we built for ZQube1, and that was refined and went through a few different revisions, and we currently sell that radio commercially, and that specific radio is available in UHF VHF. It's a TTNC radio, so it's UHF VHF, and then we have a half duplex UHF radio that operates in. And you can choose we build one for amateur and one for commercial frequencies. Then we developed a S-band payload transmitter that was specifically built for UCube1, the UK Space Agency's first satellite, which was a CubeSat. And then I think towards the end of last year we developed an X-band payload transmitter with a company called ETSI, Electronics Diamond Stellenbosch. Then we also now build payloads where we build two payloads for ZQube2, which I'll talk about a little bit more in a few slides' time. But the one is a software-defined receiver specifically for AIS messages, and the second one is a fire detection camera. The AIS receiver we did in collaboration with a company called Stone3, and then the fire detection imager was built with the help of the CSR. Then sort of the other side of what we do is the mission side, where we built ZQube1, which was launched in 2013, and then ZQube2 at the end of last year. ZQube1 was a 1-unit CubeSat, and then ZQube2 was slightly bigger, a 3-unit. So ZQube2 was meant as a precursor to a bigger constellation, where with ZQube2 we wanted to demonstrate the technology behind AIS and VD message reception. VD is sort of the next revision of AIS, and that is our primary payload. And then we wanted to demonstrate this novel fire detection imager, which we carried as a hosted payload. The slightly smaller pictures on the left is the software-defined radio, which is a rework of the company Stone3 as a terrestrial AIS receiver that they developed. And we basically reworked the terrestrial receiver with tweaks to the RF front end and the code that we need to interface it with the satellite, which then became the software-defined radio payload for ZQube2. And the K-line fire detection imager we did with CSR, because they have a lot more experience than us in building optics for space. So they helped with the optomechanical part of it, and we did the electronics behind the imager and interfacing that with the platform. And then you've also seen that we've kind of undressed ZQube2 on the right-hand side, so that you can kind of get an idea of what it looks like without the panels on. So the other parts that make ZAQ2 work is as part of the platform is we use one of our UHF TT&C radios, and we also have both our payload transmitters. So we have the S-band payload data transmitter and also the X-band one. The S-band is our newer one, which operates at 10 megabits a second over the air, and X-band can go up to 50 megabits a second over the air. And it's actually quite tricky if you start thinking about to feed these transmitters with that amount of data is quite a tricky thing. Then with the help of a company called CPUT Space in Stellenbosch, we use the ADCS system, which means we're 3-axis stabilized because we need to point our cameras and our antennas to the ground. And CPUT Space is a spin-off company from the University of Stellenbosch. And then something that we might explore in future is the ZAQ2's flight software we can actually reprogram in flight. It's a bit of a pain, but it is possible, so I think we might explore that once we've operated the satellite for a bit and shown everything that we wanted to show. And then phase 2 of the current project would be the constellation, which I think they have subsequently kind of announced, which we are now contracted to build a few more CubeSats with regards to maritime domain awareness and AIS message research. So once the satellite was built and tested and we were happy with it, that was ready to go, we shipped it off to Delft in the Netherlands, where we did some final checks before it was integrated with its launch adapter. So on the left hand side you can just see one of the little setups that we had to do some checks, and then the top right is what the quad-back deployer looks like without the satellite in, and you can see the pusher plate with a spring behind it, and then at the bottom right you can kind of see the satellite halfway in the deployer. So that the spring that you can see actually doesn't have a lot of force. If you push the satellite in and you release it, then it kind of pushes out to where you can see at the bottom. So it's a very gentle push that it gets, because you don't really want the thing to fire it out of the launch adapter, because then you end up with the thing tumbling quite violently. And we were quite lucky enough that we saw the rates that the satellite was released with was quite low. So by the time we switched on the ADCS and started measuring the rates, we weren't really tumbling at a very high rate, which was quite nice for us. Then we, from the Netherlands, the ESA ships it to Russia, where it's integrated with the launch adapter. And on the left-hand side, you can kind of see one of the quad backs over there, where it's mounted on top of the rocket. And then this weird South African flag on the fairing, which was quite nice. And then we were launched on top of a Soyuz from sort of the east of Russia, very early on the morning of the 27th, and I've not really slept since then. Then on the ground side, we were lucky enough to have 2 ground stations at our disposal. The primary one is on campus at CPUT, and then we were working with Space Tech in Hartech near Grabo. They used to be the old Sun Space, and we helped them with the bits of hardware that they needed to get their ground station to run, which I think is nice for them, because they have subsequently been able to make contact with what's left of Symposium. So it's nice in the fact that it helps us a lot, and it's also useful for them to have their ground station up and running again. So our ground station, the satellite operates on commercial frequencies. So it's one of those CubeSats that's not on amateur frequency, which is a bit of a pain, because it means that you can't really readily go and buy something off the shelf. The receive site's nice because you have loads of STR receivers that you can use. And as a matter of fact, through a few different decisions, we ended up using a FunCube dongle. But a FunCube dongle with the asterisk, because it's a specially selected FunCube dongle that we're currently borrowing from Space Tech that they got for Symposium, because the normal FunCube dongles don't really work at the frequencies that on the commercial band. There's a gap. So these are specially selected to kind of work there. I think the older ones do work there. And then on the transmit side, we've got an ETIS USRP radio. And then on the software side, we use GNU Radio and SpaceX mission control software for the receive side, which works quite well because we can very easily compare what we see at our ground station to what SpaceX sees at their ground station, because it's similar setups. And then just some issues that we've been experiencing is load shedding is a bit of a pain, because at the moment we don't really have all our UPSs set up. So every time the power goes down, you kind of need to go in and start everything up and make sure that everything runs. And then we've also had a bit of an issue with RF interference, where with the SpaceX software that we're using, we can very easily build stuff on top of that. So we were able to write a script that measures that you can command the ground station antenna to do a sweep at 0 degrees elevation, the whole 360 degrees in 1 degree steps, and then you can measure the relative RSSI. So it means that we can kind of do a survey of the RF environment at the frequency that we're working at and see how that changes over time. Which we did to show that we had an issue with RFI, but it also showed us that this is actually a really good tool, and I think we're going to have nice data if you do this quite regularly over a period of time, which is what the graph shows. So the red and blue line shows sort of two sweeps done just after each other, and you can kind of see on the right hand side of the graph, you can see there's something was pulling the noise floor right down, and there was a nice gap until you scanned out of it again. And then we could also see that while we were operating the satellite, you can just see that everything was suppressed, and then at some point it disappeared, and then we did the yellow and green line is another two passes done just after each other, which showed that's gone away. So we didn't really have a lot of time to investigate the signal that was interfering with us, but this gives us a tool to kind of monitor and benchmark it. So if you see that things aren't looking that nice, then you can do a sweep and you can kind of see if there's any issues. Then getting to some of the data that we've gotten back from the satellite so far. With CPUT, we do a whole load of what we call whole orbit data logging, where we log quite a few parameters from the satellite bus, literally I think every 3 minutes at this stage, which allows us to download that data, and then you can get different trends that form off through as the time progresses. So we can kind of see if the temperatures go up slowly, or we had a thing where I think one of the temperature sensors on the battery kind of started showing weird values, and then you could see that over time it was fine, and at some point it jacked right up, and then it dropped back down again, which we didn't see in any of the other sensors. So it looks like it might be an issue with the sensor. So what the specific graph shows is just a few different temperature sensors, which you can see all kind of tracks each other, and the bottom end of that graph goes from the bottom of the blue line is kind of 0, so you can see that kind of swings from, I can't even see what's on it, from that's about 20 degrees to the bottom would be 0, so you can kind of see it's not a big swing, and this is over about 5 passes worth of data. And then the blue line is just something that shows the transmitted packet counter. So then you can see there where the blue line does 2 jumps is where we had 2 overpasses. And then obviously the receive message counter increments as soon as you start communicating with the satellite. And this is just some more of the whole orbit data, where the bottom line is the battery voltage. And this is also for about 6 overpasses, where you can see during the sunlit part of the orbit, we basically dead on 8.2 volts, which is full charge for us, and then as soon as you go into the eclipse, then you can see the battery slowly discharging, And I think at this stage, this battery voltage is about 8.1 volts. So I mean, we're not that, I think this is literally just after we were launched. So I mean, we don't have a lot of things switched on. So then you very quickly return to full charge, and then you slowly start discharging an Eclipse. And the top telemetry is I think the total current that we get from the solar panels. So you can see that when it's in Eclipse, you obviously get no current from the solar panels. It jumps fairly quickly and then tapers off, and then when you Eclipse, it's down to zero. Then it took us a few weeks to get into the commissioning of the ADCS. We've got quite a few graphs and quite a few things that we went through, but I think this is a nice graph that kind of illustrates what happened. What you see on this graph is the estimated angular rate, so that's sort of in degrees a second, which means how fast the satellite's spinning around all three of its axes. And the process that we go through is initially when the satellite was released, it was free tumbling until we switched on the ADCS, where the idea was to detumble it into a spin around the y-axis. So the y-axis would be the long one, so if that's the satellite, then it would spin around the long axis, which was the idea. And then this is kind of shows, as soon as we started doing that, where on the left-hand side, the red line is the y-axis. So you can see the blue and the yellow, which is X and Z, that dampens to around 0 degrees, and you can see the red line creep down to -2 degrees, which is the set point. So we want to be spinning along the y-axis in a certain rate. In this case, I think it was -2 degrees, so I think that's probably backwards, because the final step that we needed to do is we have a momentum wheel that's mounted in that y-axis. So as soon as you switch on the wheel, then the wheel absorbs all of that momentum, and your satellite ends up flying straight, which is what we want, because we want our cameras to point down and our antennas. So as soon as you have your satellite stabilized, and I think we even did that before the satellite was stabilized because I couldn't wait. But this just shows some of the first AIS data that we received using the software-defined receiver. That's obviously a map of Africa and Southern Africa, and each dot represents a message that we received from a ship. So every ship above a certain tonnage has to carry this AIS transmitter that periodically, depending on how fast the sailing, transmits AIS messages. And these are the AIS messages that we receive. So these AIS messages are often received by stations on the coast, but as soon as the ship goes into the ocean, then you can't receive those messages anymore. And then people discovered that you can receive these messages from satellites. So that's basically what each dot represents. So that's a message from a satellite that we saw, and we could say that that's where the ship is reporting that it's transmitting from. So as soon as you have that data, then you can do a whole lot of things, and if you have data from every day or a continuous data set, then you can do interesting things with that data. The right-hand side map is one that we did a couple of weeks ago, which I think we commanded it to switch on when it was fully kind of fairly high up Africa, because we wanted to see sort of what we can see high up in Africa. So that's why you can see dots all the way, I think, like too close to the equator. And then this one was, I think we did on Monday, which we started the reception session quite far down south. I was hoping we could maybe see something over in the Antarctic, but we couldn't. But we did see is the ship that these dots represent was the SA Gallus, actually, I think, returning from the Antarctic. So it was quite nice to go and see, because we just get this identifier, and at the moment we don't really have anything that's automated, so you kind of have to go look at the ID, go and look it up on the internet. It's like, oh, it's the Gallus. And I think that's when it kind of hits home that that thing that you worked on is up there, and you're kind of receiving message. I mean, obviously these are all real ships, but I think the SA Dallas is a ship that we know with us. And at this stage, we've only kind of tested it over South Africa, but we're able to switch it on when it's not over South Africa. So we'll be exploring that a bit more. And then I think literally this week we were able to kind of start releasing a bit more of the data that we started to get from the K-line imager, where we had to go through a bit of a process of tweaking the configuration a bit, because we kind of started getting completely white images from the white camera, and then you kind of go, well, there's not an issue. But then it ended up with the pictures were just massively overexposed. So you ended up with a white picture, and then as soon as we dialed that back again, you could kind of start making out features, and I think we're now to a point where we've got a better handle of what the setting needs to be. And we should be able to get a bit better data from the imager. So that's a 3-image scene from one of the cameras, where you can see the 3 images where we've kind of aligned it, where as soon as we tell the imager to start imaging, then there's different settings, but at the moment the way it's set up, it takes 2 or 3, or it takes 3 successive images, and then it stops. And this is basically what you see here, where we have 3 successive images, and then it kind of also gives you a bigger spot to kind of figure out exactly what you're imaging. And this is of the Full-Flay Dam in the Western Cape, which is the black spot that you can see there. And then this is from the one camera, but the other camera also gives you images that look very similar to this. All the images that we generate are in this black and white grayscale sort of color scheme, and then the idea is to overlay those images, and then you can do processing and figure out where the fires are. And then that's like, we couldn't really do the satellite without all the partners. It's quite a complex thing, and on the ground side and all the things that you have to do, you kind of need a few people other than just us to make it happen. And then I guess if there's any questions.
You said that you couldn't quite get that you send down your data every 3 minutes, or is it recording data every 3 minutes?
So it's recording data every 3 minutes that we log to a channel on board. And at the moment we're only really operating over UHF, so we're kind of literally drowning in data that we need to get down. But the platform logs every 3 minutes, which is adjustable, and we can also adjust what it logs. So at the moment it logs to onboard flash, and then that we retrieve when the satellite's over the ground station.
And that 3 minutes was basically arbitrarily chosen?
No, so it does every 3 minutes. We've got a list of parameters that we want to log, and every 3 minutes it takes a log of all those values. So we've got battery readings every 3 minutes since the 27th of December, if that makes sense.
Don't you use obvious hook at all? I know that was one of the SA sets.
No, I think we did approach them, but their ground station that we would be able to use, I don't think is really functioning at the moment, because I think they built that for Simbandila, and then I don't think they kind of kept it working after that, which was quite a few years ago. But I think we chat to them every now and then, but we're not actively using them at the moment. The nice thing about the mission control software that we use from Space Tech is they inherently allow us to use more than one ground station quite easily, which we aren't doing, but we're kind of working with them to figure out at least how we can use our ground station and the high-tech one, so that you can use data received from both of them. So if we send a command and we don't necessarily decode the response to it, and they do it, that we just transparently see the response. But we're not there yet, and that's a lot of work that Space Tech needs to do. But it's nice to be working with them because it easier allows us to do stuff like that, but we're not really using hypervisor at the moment. There's somebody over there.
Just the AIS data, you're only recording over South Africa. Is the limitation the download or is it the storage on board? Why are you not?
At the moment, it's because we're literally telling it to switch on over South Africa because it's over South Africa. If you want to operate it when it's not over the ground station, then we can schedule certain things to happen when it's not over the ground station. So it's purely because we're kind of testing things out, and we're sort of interested in the AIS data around the South African coast, but we can operate it where it literally, the way we're using it at the moment, it wouldn't matter if it's over South Africa or not over South Africa. We just need to schedule that operation to happen.
What frequency does it operate on, and do you have to worry about Doppler at all?
So we on UHF, so it's around just over 400 megahertz, I think.
Is that the AIS?
Oh, the AIS. Sorry, the AIS is 162 megahertz, so yeah, you have to worry about Doppler.
So does your SDR take care of that?
Yes. So the SDR has, I'm not exactly sure how they set it up, but they have the SDR, I think they have multiple SDR receivers. There's 2 channels, but they have multiple receivers on each channel, and I think each one is, its receive bandwidth is broad enough to, so that you can receive that signal even with the Doppler.
FM-based broadcast?
I think it is FM, I'm not 100% sure. But so far we've been, the receiver seems to work quite well, and we even managed to, the Stone 3 has a few test transmitters that they run from Somerset West, and over one of the last overpasses we actually managed to receive one of those test transmitters, and I think they're quite small.
And the interval between these beaconing from the ship, right, is it too long so that you can command the satellite to switch on the receiver and for a pass, right? Do you catch all the ships that are there, or is it kind of a bit of a gamble because you don't know when the ship's going to next send?
That's kind of tricky to say because I think it has more to do with the RF side of it. For instance, I know because I went and checked for the SA Gullis, we received 10 messages, and if we plot those messages on sort of Google Earth, and then you can see its little track. So the rate at which the AIS transmit depends on what the ship's doing. If it's under engine or under sail or above a certain speed, then it needs to transmit at a higher rate than what it is in at anchor.
Is it a high rate guarantee you're going to get a transmission in a 10-minute pass before Australia?
Yeah, no, definitely. I don't think a lot of the messages that we receive, you receive multiple messages from one ship.
On a single pass?
No, literally from 2 or 3 minutes. A lot of these reception sessions happen over literally 2 or 3 minutes, and in 2 or 3 minutes you receive multiple messages from a ship. But that's sort of something that we must all do, is try and correlate what we receive to, but now you need a commercial AIS message source because you need to compare it to kind of something that you know is close to what's actually happening, and that's kind of another whole exercise.
Okay, Leon, thank you very much for a very interesting presentation. Somebody missing some funny blue pen? Nothing, I'll leave it here up front.